All right, it has started recording. Oh, Shadet's here as well. Okay, alrighty, let's go.
Okay, hello, can you all hear me? Yep, okay. Okay, thanks Edmund for organizing. So today we'll talk about these monster and some categorification stuff on it, like how they discover the monster group. Monster here refer to monster group. So this is just some sharing seminar. So there's not much technicality I will dwell in, and mostly we will emphasize on idea flow and how the theory are connected. And I will share some history. And if you have any question, you can ask during the talk. If you miss something or I hide something so that you don't understand, then you can ask. So basically, I'll give an overview of the talk. So how I come across this monster group. So my PhD project is mostly dealing with categories that after you decategorify or you take the Grothendieck group, it will give you some classical matrices or polynomials. For example, the Coxeter matrix or the Jones polynomials. Okay, and I come across these categorified VOA, vertex operator algebras. So I was curious about this VOA. So I go and search for its history. Actually, this VOA can be considered as a representation of a monster. Okay, and this monster group is coming from a group theory, and some other guys found some function in the number theory called the J function, and see some relation between these the representation of monster and this J function by taking the character of your representation. Okay, so this is like how these monster connecting these three main subject in mathematics. So let's start with number and group theory. Okay. So in numbers, you want to break down the numbers into a further atom. In chemistry, they break down compound into elements. So what's the elements in numbers? They are the primes. How about groups? Group has analog, has the same analog, which is the simple groups. Okay. How are they useful? So every number can be written uniquely as a product of primes. This is the fundamental theorem of arithmetic. And on the other hand, there's a Jordan-Holder theorem for groups. You can have a filtration for your groups in terms of normal subgroup. But bear in mind that this normal subgroup, you do not require each GI to be normal in the big G. Okay, it's just consecutively. But in numbers, every primes can divide n. Okay, this is the difference. So that's why maybe this is why this is not called a fundamental theorem here. Moreover, if you have more than one composition series, they should have the same composition factors when you take the quotient. Okay. For example, look at the 12. Okay, 12 you can write as a 2 times 2 times 3 or 3 times 2. This is regardless the rearrangement. So similarly, you can look at a cyclic group of order n, order 12. Okay, so why I write 0 here in terms of 1 here should be clear that the group of composition is 0 here. Okay, so 0 is the identity element. So, okay. Any question here? Okay, no? Okay, so far so good. So next. So it's proven by Euclid that using the +1 proof, you can see that the number of primes is infinite. Of course, this is also true for the finite simple group. But in around 1980s, spread over 15,000 of journal pages and 500 individuals, and the final proof is 4,000 pages that prove the classification of the finite simple groups. Okay, they are, okay, I already list down all of them here. So these are cyclic group, alternating group AM, and then the group of Lie type, and then sporadic groups. So these sporadic groups, they don't belong to any groups, any other groups. They are not classified. So they are isolated. So they are sporadic. Okay. And today we are going to look at the monster group, which is inside this sporadic group. Monster group is the largest sporadic groups. Okay. And if you notice in the bulletin today, in the afternoon, there's a quantum seminar talk on action of Thomas group. So Thomas group is actually a subgroup of monster group. It's also one of the sporadic group. Okay. And okay, so someone draw this periodic table for the finite simple groups. Okay. So monster is here. Okay. It's kind of creative. Okay. So this is making up all the groups. So today, now we will talk about monster. Okay. So why is it called monster? So this is the element inside our monster group. This is the number of elements. This is the order of our group. It's around 8 times 10 to the power of 53. Okay. You may not know how big it is. It is about the number of particles on the Jupiter. Okay. Okay. So next. So actually, why? Maybe you think, well, how this number is coming up? It's actually the product of these prime numbers here. Okay. There are actually 15 that consists of 15 out of the first 19 prime. Okay. And the only one that don't divide the monster group is the first 4 that don't divide is 37, 43, and 67. But it divides other sporadic groups. And 61 is the one that don't divide. Divide none of the sporadic groups. Okay. And then what else? 20 out of 20 out of 26 sporadic groups are subgroup of this monster. Okay, this is how big the monster is. And before this monster group is discovered or written down, they already know that it possesses an irreducible representation of dimension 196,883. Okay. And let me see what happened. Okay. And what else? And they also computed there is 194 conjugacy classes, even before monster exists. How they discovered, how they computed, they do it in a smoke-filled room in Birmingham. Okay, done by Fisher, Livingstone, and Thorne. And this is the list of it. Okay, so you see 196,883 coming up here. So be vigilant with this number. We will like frequently come back to this number here. Okay, so one row have like 60, and then total is 194. Okay, so what happened? In 1973, Fisher and Gris independently conjectured this group. Okay, but before the group come up, John McKay in 1978, he was working in the group theory, but taking a break. So he read a paper on number theory, okay? And then he saw this function here, this J function, this so-called J function, Jacobi function, okay? He saw that, hey, 196,884, isn't it close to the irreducible rep of the monster? Indeed. And then this is just 196,883 plus 1. Okay. Yeah, so he emailed this to Thomson. Okay. Thomson is the Thomson group, Thomson subgroup, that guy. Okay. He emailed this to Thomson suggesting that, hey, maybe there's a vector space associated to each number. Okay. After you compute the dimension, it's actually this number. Thomson said, hey, okay, yeah, sure. And then he twisted a bit. He said that, oh, maybe it's a character of the group that can give you, the group element that can give you this number. Okay. So what happened next? And in 1981, Greece, he conjectured first, right? And then he actually found this 196,883 irreducible rep for this monster to add on. Okay. In the paper, actually, he called monster the friendly giant, but no one used it. So we still stick with monster. Okay. And yeah. So okay. So next we will go to J function. So this number theory. So what does it to do with this J function? How interesting is this J function here? So let us look at SL2Z. So SL2Z add on the hyperbolic plane by the Mobius transformation. So let's write it down. So like this. So A is a matrix in SLZ. Okay. So there's an action of SL2Z on the hyperbolic plane, where these are just points with imaginary number, with imaginary part greater than 0. So also you can consider a discrete subgroup, or sometimes they call a fusion group. Fusion, or some kind they call discrete subgroup. Okay. This subgroup is not very important, but you just need memorize there's some congruence group. That's interesting here. So, but we also look at the normalizer of the subgroup here with this. Okay. So if you look at this hyperbolic plane mode out by the action of SL2, it's actually a genus zero surface. Okay, what does it to do with genus zero surface with this J function? So when this surface is 0, actually every holomorphic function on this genus zero surface can be expressed in terms of one rational function, which is the J function. Okay, it's like a basis, something like that. It's like every periodic one function can be expressed in terms of e to the it. Okay, so this J function is something like that. So since genus 0 is very important, when is this group a genus 0? So in 1975, Ock in France say that he proved that only for this kind of prime you can get this surface to be genus 0. At the same time, he also attended a lecture by Tix. Tix is describing the monster to people, where the orders are product of this prime. So there's a coincidence here. So Odd say he will offer a Jack Daniel for those can expand this relation. Okay, a $50 worth. Okay, so yeah, so it's around here. So let me see. It's even before John Mackay see the Mackay equation. So around here. Okay. And okay, so why is this important? So whenever this J function can help express the other rational function, holomorphic function, we call it a half module. Okay, so half module. In particular, when we look at the hyperbolic plane model by SL2 action, the half module associated is exactly this J function that Mackay looks at. Okay, but for representation theory purpose, for our constructing the vector space, we look at this by taking away the constant term. Okay, this is V0, V0. Okay, so this, yeah, so you should think that there's like a V minus 1 here, V1, V2, V3, and so on. Okay, this function is going on and on. So they call it a moonshine relation here. So moonshine is like a silly talk, okay? Because you can't just say that something have a relation just by looking some number, similar number, right? But in fact, in representation theory, if you ever met an interesting natural number, you should ask if it is a character degree of some representation. This is the philosophy behind categorification. Categorification. Okay, so yeah, so this is what most representation theorists do nowadays. So okay, the first persons or two persons, Conway and Norton, collect all this data. They go back and compute what Thomas say, and they come up with this monstrous moonshine conjecture. Okay, in the paper. So first of all, they say that there's a function. There's a function for every element of monster and some representation such that the coefficient is the character of that representation. Okay. Actually, they check it for a first view coefficient. And Conway described that as the most happiest, like the happiest moment in his life. He went down, he checked, he found the character, and then he go down to the library and search for the 100 boot on Jacobi modular equation. He found that matches. So after that, they come out with this monstrous moonshine. Not only that, if you look at other different element in the group, in the monster group, actually the TG is Jacobi half module for the particular modular group when you substitute P with the order of P, with the order of the element G. Okay, so it's the half module for different genus zero surface, which is this. Okay, and then what else? Yeah, so this is like how they check it. You can see that actually you can see, what can you see? So 1 is just 1, and then this is the 196,883 plus 1, and then this number here is this plus this plus this. So let me write down. So let's say this is V minus 1, this is V1, so this is V minus 1 plus V1, something like that. Okay. But actually, you can see that there's 994 conjugacy classes in M, but there's only 171 distinct McKay-Thompson series. Okay, this is part of the conjecture. So how to tackle this conjecture? So in 1981, Greece just built a we call it a Greece algebra that he wraps. Then he proved that monster is actually the automorphism group for that algebra, which proved that like it's acting faithfully on that algebra. And so Frankel, Lipovsky, and Mermer come up with this moonshine module. So what's the moonshine module is? So moonshine module is a direct sum of finite dimensional vector space. Okay, and it is a z-graded. Okay, and then what is in there? The most distinguished one is the vacuum vector in the v-1, and everything is finite dimension, and then v-1 is one dimensional. Okay, and then v0 is 0, where we throw away the constant term, right? So v0 is 0. And then actually when they so for every v in this moonshine module, you can associate a linear map. This is where the vertex algebra comes in. So every vector you associate an operator, right? So how you associate this operator? This operator is actually built up by Vn, and each Vn is an endomorphism of this bit vector space. Okay, and so this is called the vertex operator associated to V. And there's one distinguished element called the conformer or Virasoro vectors. So I explain this because I keep reading stuff on this. So now I get the relation. So conformal vector V, you also can look at the associated vertex operator. Okay. So this Wn is the coefficient of these, you can call it Lorentz series. They generate a copy of Virasoro algebra with central charge 24. Okay, I will explain what this means. So first of all, let me write. Okay, so what is a Virasoro algebra? Virasoro algebra means if you look at the commutator, okay, they will have this relation, adding up relation, and also creating a central term here. This is the coefficient. This is some vector.
You're just off the top of the screen.
Okay, sorry.
You
Can't see.
Yeah, that's better. Oh,
is it okay?
No, you're back to. I can see the 12. I can't see what's above the 12.
You can't see above the 12. Oh, okay. Let me move it down. Now? How about now?
Yeah, that's good. Thank you.
Okay. So what's the time now? Okay. So yeah. So let's talk about weak algebra first. So let's draw a line here. So this is Virasoro algebra. So weak algebra, what is weak algebra? So weak algebra is just the same commutator, but only give you the front part. And Virasoro algebra is this weak vector plus a central extension. Okay, it's a central extension of weak algebra, which means V is equals to weak plus C. Okay, so this C is a central of V. So this C will commute with everything in V. And so you can see that if you send this C to 0, you can recover the weak algebra. Okay, so when you send C to I assume there's some canonical C you can pick here, where this C should be 24 if we look at our vertex algebra. Okay, this 24 is quite interesting, right? So this VOA is actually built out using the Leech lattice. 24 is the dimension of Leech lattice. And Leech lattice is built in 26 dimension. Okay. 26 dimension is even more interesting because that's the only dimension that string theory can be defined. Okay, so this is like the first example they come out with for string theory. And yeah, so there's also a story that after you apply some supersymmetry, you get super string theory, where you can supersymmetry. Oh, the screen back on. Okay. So you can reduce this dimension to 10. So 10 is 4 plus 6. 4 is 3 plus 1. R3 plus 1 dimensional time, and then plus 6. So after this supersymmetry, you might wonder, what's this 6th dimension here? It's actually the Calabi-Yau manifold. Calabi-Yau manifold. Okay. And there's some mirror symmetry among this Calabi-Yau manifold. Okay. Yeah. Okay, so these actually the moonshine module, every single part of them is finite dimensional. And only you can think that only 900, let me write it down, 906 conjugacy classes. And you already know that this means that there's only 196 EREP. Okay, for monster. So how they come out with this infinite representation? They are just direct sum of EREPs. Okay, and this direct sum turns out matches up with the coefficient of J function. Okay, that's the story. And but actually Frankel and ETAL, they don't really prove that all the character matches up, because to check you need to do all the calculation. But Brochard come up with one brilliant idea, which allowed you only to check a few terms of the coefficient. So what Brochard do is he constructed a thing called monster Lie algebra, okay, which is a generalized Cox-Moody algebra. So Cox-Moody algebra is a generalization of Lie algebra, and Brochard further generalized it to include imaginary roots. Okay. And what's the benefit of constructing this Cox-Moody Lie algebra? In this way, you can use the character formula or the denominator formula to get a combinatorial recursion of relation between the coefficient. Okay, you know what coefficient coming next using the first few. And then this relation only determined by a finite number of coefficients. Okay. And on the other hand, J function of the half module also belong to a class called replicable functions. They also have recursive relation between coefficients. So both of them have recursive relation. So they just need to mesh up, right? So actually they mesh up. And now we need to check whether the first few terms are the same or not. How many terms they need to check? They just need to check the first, second, third, fourth, and sixth coefficient. Then he's done. Okay. And then because all all of his work, he get a few medals. And Borchardt is actually a student of Conway who conjectured the monstrous moonshine. Okay, yeah. Yeah, so probably we will end here. Okay, thank you.
Okay, any questions from the audience? Okay, I probably have one. Kising, so towards the
Yep.
end, the way that brochure like the thing that brochures proof was actually Conway's monstrous moonshine
Yep.
conjecture, right? Where
Yep.
the character and the J function matches up.
Yep.
Okay.
Yep. Yep. But okay. Actually, the story is long here, but I just suppress it. So the hard thing is to create this generalized cut-smoothie algebra. So cut-smoothie algebra already has the denominator for formulas. Borchardt wants this formula to hold in this monster Lie algebra. So he created this generalized cut-smoothie algebra and come up with this formula here. And also he's not getting few medal by just proving this monstrous moonshine conjecture. Actually, he created a few, which is generalized cut-smoothie algebra, and also he axiomatized VOA. Yeah. So there's two big things he done before boiling down to just checking this 5 coefficient here. Yeah.
Is there a simple way to understand how the monster Lie algebra is related to the monster group? I mean, like, does the group act on the Lie algebra in some way, or?
Yeah, it is.
Okay.
And
Okay.
yeah, it is. Yeah, the way they act on is should be these what is it? Should be this. You have relation between these coefficient, right? Wait, yeah, this coefficient. So actually, every VOA will give you a Virasoro representation because these operator naturally satisfy the relation. Yeah, and how they get the VOA actually quite similar to Greece algebra. So how they, since there's time here, right, we can talk a little bit. So how this Greece come up with this Greece algebra? Actually, he looked at one big subgroup C inside the monster, and then he just introduced another involution. A priori, he don't know that this is the monster, but he collect all the monster character. I mean, not the character theory character, but the properties, and then he go and build this erect, and then finally he showed that actually these two generate monster. Yeah.
So when you're taking C, like, you're taking the
Subgroup
I'm assuming you're taking the
one
subgroup C, and then you're taking the group ring and have
big,
some involution with it, or I mean, you're trying to build an algebra, right? So
yeah, right.
Okay.
I mean, yeah. I mean, these are the this is a big subgroup inside monster, and then this is the involution of monster. Yeah.
You're off the top of the page again.
Oh, okay.
Just slightly.
Maybe I move it down.
Thanks.
I move it. Yeah, I move it down. Let me move it down. Yeah. Yeah. Yeah, the way they build this Grease algebra also, they break it into several parts. Yeah. It's quite interesting how they find this monster group. Yep. Bradley, you got anything to ask? Yeah.
Right, any other questions from the audience? If not, then I can probably just stop the recording first. Let me do that.